Hello, my name is John Moyer, and I want to welcome you to the NIH Office of Disease Prevention's Methods Mind the Gap webinar series. This series explores research design, measurement, intervention, data analysis, and other methods of interest to prevention science. Our goal is to engage the prevention research community in thought-provoking discussions, to promote the use of the best available methods, and to support the development of better methods. Before we begin, I have some housekeeping items. You can submit questions during the webinar via the chat pod. You'll need to open the pod by hovering your cursor at the bottom of the Zoom window and then clicking on the chat icon. Please direct your questions to hosts and panelists. We will open the floor to questions that have been submitted via the Zoom chat pod at the conclusion of today's talk. The slides and video recording will be posted on our website, prevention.nih.gov/mindthegap, in a few weeks. Lastly, we would appreciate your feedback about today's webinar. Upon closing, you will be asked to complete an evaluation. We would appreciate your feedback as it will help us improve this webinar series. At this time, I'd like to introduce Dr. David M. Murray, Associate Director for Prevention and Director of the Office of Disease Prevention.
Thank you, Dr. Moyer. Today's speaker is Dr. Kelsey Grantham. Dr. Grantham is a research fellow in biostatistics in the School of Public Health and Preventive Medicine at Monash University in Melbourne, Australia. With a background in mathematics and applied statistics, and after working as a mathematical modeler in disease epidemics, she commenced a PhD at Monash focused on developing statistical methodology for cluster randomized trials. During her PhD, she developed new, more realistic statistical methods and more efficient trial designs, which have helped ensure that cluster randomized trials draw valid and precise conclusions about the impact of new interventions. Her PhD was awarded in 2021, and she received the Damien Joly Award for an outstanding doctoral thesis. As a postdoctoral research fellow, Dr. Grantham leads research on efficient and less burdensome cluster randomized trial designs with a focus on staircase designs, and also leads the statistical aspects of applied studies at Monash. It's my pleasure to welcome Dr. Kelsey Grantham.
Thank you very much for the introduction, Dr. Murray. So today I'll be sharing some insights into the efficiency and benefits of staircase cluster randomized trial designs. I'll start by giving a brief introduction to cluster randomized trials, stepped wedge designs, and staircase designs. And then I'll get into some of the work that I've led on staircase designs, including some of the underpinning statistical theory for the designs, some comparisons between staircase and stepped wedge designs in terms of efficiency, and also looking at which staircase design variants are most efficient. In a standard randomized controlled trial, we randomize individual participants to intervention and control groups to test whether a new intervention or treatment works. So we may be testing a new drug, and half of the participants are given the new drug and half the placebo, and then participants' outcomes are compared to test whether the drug is effective. But in some situations, the intervention of interest naturally applies at a group or cluster level, such as if we were interested in testing whether a new cleaning procedure in hospitals reduces hospital-acquired infections in patients. And so a cluster randomized trial must be conducted to test the intervention. The defining characteristic of these trials is that we expect that the outcomes of participants within a cluster are more similar to each other than to participants in other clusters, and we must account for this similarity when we set up the trial and when we analyze the trial data. And because the intervention naturally applies to the cluster, we must randomize entire clusters rather than individual participants to the control or intervention condition. There are different possible cluster randomized trial designs. The simplest is a parallel design where half of the clusters are randomized to the control and half to the intervention. But this design is not particularly powerful in some settings, meaning we would typically need to involve a lot of clusters and participants in order to detect an intervention effect. And in many settings, it's also not very appealing since half of the clusters would never get to implement the intervention. There are more sophisticated designs that can deliver greater study power and are more appealing, such as the stepped wedge design shown here. And with the stepped wedge, each sequence or row in the schematic starts in the control condition and then switches over to the intervention condition in a staggered manner until all clusters implement the intervention by the final period of the trial. So from the first period of the trial until the last period, clusters contribute data by measuring participants' outcomes. In some settings, these participants may be measured more than once, as in a cohort study, but in this talk, I'll focus on settings where each participant is measured just once and new participants are entering the cluster in each period. So we typically depict the design schematic like this, where each cell represents a cluster period and contains either 0 for the control condition or 1 for the intervention condition. A particular design has several identifying characteristics, such as the number of unique sequences, the number of clusters per sequence, and the number of participants measured in each cluster in each period, otherwise known as the cluster period size. Stepped wedge designs are a popular choice and are widely used, with over 500 stepped wedge trials currently registered on clinicaltrials.gov. These are appealing designs since all clusters eventually receive the intervention, and the gradual rollout of the intervention across clusters can make it more logistically feasible to introduce an intervention over time across different sites. These designs are typically more efficient than parallel designs, since they can make use of within cluster as well as between cluster comparisons. But one major disadvantage of these designs is that they can be burdensome and expensive. All clusters must contribute data in all periods of the trial, even for clusters that won't get to implement the intervention until towards the end of the trial. And this is problematic for many prospective trials, particularly when data collection is very onerous, invasive, or expensive. And this can make some stepped wedge trials infeasible, where the trial can't be conducted, the intervention can't be tested. And so less burdensome designs are needed that make more efficient use of trial data. And over the past 5 years or so, a new class of designs has emerged that seems to fit the bill. A body of statistical work around the information content of cells in stepped wedge designs showed that cluster period cells in certain regions of the stepped wedge design contribute more information than others about the intervention effect, and some cells contribute nothing or very little. Specifically, cluster periods close to the time of the switch from the control to intervention conditions contribute the most information. And typically, the cluster period cells more distant from the time of crossover point don't actually contribute much information towards estimation of the intervention effect. And so this work suggested that we could potentially remove some cluster period cells from a stepped wedge design, resulting in an incomplete stepped wedge design, without much of a reduction in statistical power. And in recent years, researchers have started using incomplete stepped wedge designs in settings where a complete stepped wedge would have been infeasible. One example is a trial that wanted to test whether a new intravenous catheter flushing education program would reduce the incidence of all-cause catheter failure in patients across several hospital wards. They used the design depicted on the right because they wanted to have a staggered rollout of the intervention across the wards, and they also needed to minimize measurement burden, as they had a complex outcome measure that placed extra demands on staff, and it would have been overly burdensome to require data to be collected for all periods of the trial. Another example of an incomplete stepped wedge was a trial testing whether an education program to improve self-regulation could reduce students' disruptive behavior across schools in remote Aboriginal communities in Australia. The outcome measure was a teacher-rated questionnaire measuring students' disruptive behavior and required that the questionnaires be administered in person and collected in person. The data collection was fairly onerous and time-consuming. The researchers stated that the burden of data collection on participants would be too great in a stepped wedge trial, and they also noted that it would have been too costly and also infeasible geographically to require each school to be involved in all periods of the trial. And an incomplete stepped wedge design was also used in a trial testing whether a new integrated care management model could improve quality of care in frail adults across nursing homes in South Korea. The researchers stated that nursing homes were incentivized to participate in the trial, knowing that they would eventually receive the intervention. And they also required a design with staggered rollout across the nursing homes. And they needed to minimize measurement burden, since the quality of care outcome that they were interested in was time-consuming to measure. So with statistical work suggesting that incomplete stepped wedge designs could be efficient alternatives, and the fact that incomplete designs are already being used, but in the absence of a lot of dedicated tools to support their use, I then began to more closely consider a class of incomplete stepped wedge designs called staircase designs. These designs are made up of a limited number of measurement periods in each sequence with control periods followed by intervention periods. And the data collection is staggered over time across sequences. The grayed out cluster period cells in this schematic indicate cluster periods in which no measurements are taken. So staircase designs are potentially more appealing to participating clusters than stepped wedge designs. For one thing, each cluster would receive the intervention sooner upon commencing data collection, and these designs still have the same gradual rollout of the intervention across clusters as with a stepped wedge. These designs are less burdensome since clusters only need to contribute data in a limited number of periods rather than in all periods of the trial. But there were some big questions around staircase designs that we needed to answer in order to understand them and be able to recommend them, including how efficient are these designs compared to stepped wedge designs, and among different staircase design variants, which ones are most efficient. And by most efficient, I mean which ones make best use of trial data to precisely estimate the intervention effect. So as I said, many different staircase design variants are possible, and there's currently no guidance on which ones are best. I've called the design on the left, with one control and one intervention cell in each sequence, a basic staircase design. We could allocate an equal number of clusters to sequences, or we could potentially have an unequal number of clusters allocated to sequences, as in this second design here. And then when we move beyond a basic staircase and consider staircase designs with more than 2 measurement periods in each sequence, then we could potentially have a balanced staircase with an equal number of control and intervention cells in each sequence, or we could potentially have an imbalanced staircase design with unequal numbers in each sequence. And so the main focus of my recent research has been to demystify staircase designs. So I first developed the underpinning statistical theory for these designs to ensure that trialists using these designs will be able to set up and analyze their trials correctly. And then we wanted to quantify how efficient staircase designs are compared to stepped wedge designs to see when they might be good alternatives to stepped wedge designs. And finally, we aim to provide guidance on the choice of staircase design variant. So first, I'll present a little bit of the underpinning statistical theory for staircase designs, but more detail can be found in the paper cited here. For most of this work, we've assumed a mixed effects model for a continuous outcome, where Y represents the participant's measured outcome, and then we have these different subscripts. So S denotes the particular sequence of the design, K denotes the particular cluster allocated to that sequence, T denotes the period of measurement, and I denotes the participant index within the cluster period. And we suppose that this measured outcome is made up of a fixed effect of time on the outcome, the treatment effect, where these XST terms come from our design schematic, so it's either 0 for control or 1 for intervention. And then we have cluster periods, random effects for the cluster period and the participant level random error. And for the effective time on the outcome, we would typically assume either categorical period effects, so assuming a fixed effect for each period of the trial, or we could assume a linear effect over the trial periods. In this work, I'll be assuming categorical period effects. And there are several possible structures that we might assume for the relationship between cluster periods, which induces a particular within-cluster correlation structure. And this correlation structure encodes information on the similarity between outcomes within a cluster. In this talk, I'll focus on just one structure, which is sometimes referred to as the block exchangeable or constant between period correlation structure. So this structure assumes that the correlation between different participants' outcomes in a cluster differs depending on whether they are measured in the same period or in different periods. Specifically, it assumes that the correlation is higher for participants measured in the same period, and then drops to a lower level of correlation for participants measured in different periods. The within period intercluster correlation, or within period ICC, is given here by rho, and represents the correlation between different participants' outcomes measured in the same period. And the cluster autocorrelation, given by R, represents the proportionate decay in correlation when we go from within period to between period comparisons. If R were equal to 1, then all participants' outcomes in a cluster would be assumed to be equally correlated. But for values of R between 0 and 1, we would get that step down in correlation when we go from within period to between period comparisons. And we commonly work with a version of this model that's represented at the cluster period mean level, as shown here. So here we've averaged over the participants' outcomes within each cluster period. And then the only main difference on the right-hand side is that the error term is now the averaged participant level random error. And so this model induces the following form for the correlation between cluster period means, which we will denote by the symbol psi. And psi is a function of 3 components: the cluster period size M, the within period ICC rho, and the cluster autocorrelation R. And psi turns out to be an important quantity in a lot of the work on staircase design so far. So we'll see psi appearing in many of the later slides. And I should also point out that we're not the first ones to consider this parameter psi, although it can be called different things in different papers. But other researchers have used this parameter in methodology for stepped wedge designs, as it's a nice summary measure of several parameters. So since psi is a correlation, it ranges from 0 to 1. And just to give an idea of how psi varies with these 3 parameters, these are contour plots of psi for a range of realistic correlation parameters, rho and R on the y and x axes, for a small cluster period size of 10 in the left-hand panel and a larger cluster period size of 100 in the right-hand panel. And so psi increases as each of these 3 parameters increases. We can see that psi will be small when the cluster period size is small, and the within period ICC is also small. And psi will be large when the cluster period size is large and the cluster autocorrelation is also large, which means that there's not much decay in correlation when we go from within period to between period comparisons. Of course, the parameter of most interest in this model is the treatment effect, denoted by theta. In order to understand the efficiency of staircase designs, we need to work with the expression for the variance of the treatment effect estimator, which is a key ingredient of sample size and power calculations. And we've taken the standard approach to obtaining a treatment effect estimate, which is with generalized least squares. We will also later see expressions for the precision of the treatment effect estimator, and this is just the reciprocal of the variance. So I derived the expression shown here for the variance of the treatment effect estimator that's applicable to a range of staircase designs. And this variance depends on a number of factors, including the trial configuration, so the number of sequences, the number of clusters per sequence, and then the composition of those treatment sequences, as well as the similarity within a cluster encoded by the covariance matrix for a cluster, and then matrices for the underlying effect of time on the outcome corresponding to each sequence. And so for any particular trial, we can use this expression to calculate the variance that can then be used in a power calculation. But for particular designs, we also derived more explicit expressions. For example, for basic staircase designs assuming categorical period effects, we can use this expression in terms of the number of sequences, the number of clusters per sequence, the variance of cluster period mean, as well as that psi parameter, which is again the correlation between cluster period means. And this expression tells us several things about the relationship between the variance and the trial parameters. First, the variance tends to increase linearly as the within period ICC rho increases, but there are some exceptions for certain trial configurations where the variance actually decreases as rho increases. Second, the variance decreases, or alternatively, the power increases as the cluster autocorrelation R increases, so as we have less correlation decay. And third, the variance decreases with increasing cluster period size, but tapers off quickly. So after a certain point, we don't get much more useful information about the treatment effect by measuring more participants in each cluster period. So next I'll cover how efficient staircase designs are compared to stepped wedge designs. We had some idea from the information content work that staircase designs would be efficient, but we wanted to quantify the relative efficiency with stepped wedge designs and assess when the precision of a staircase design would rival that of a stepped wedge. We compared the stepped wedge designs with several different basic staircase designs, including an embedded basic staircase design, which takes a subset of measurements from the stepped wedge. So we've kept the number of sequences, number of clusters per sequence, and number of participants per cluster period the same in these comparisons. And then we also considered an extended basic staircase design, which allocates more clusters to the sequences of the design so that the extended staircase would have the same total number of participants as the stepped wedge. We then looked at the relative efficiencies for stepped wedge compared to staircase designs, where we defined the relative efficiency as a ratio of the precision of the treatment effect estimator for the staircase design to the precision for the stepped wedge design. So a relative efficiency greater than 1 suggests that the staircase is more precise or more efficient than the stepped wedge. And so here we have the relative efficiencies for stepped wedge compared to embedded basic staircase designs with 3, 5, 7, and 9 sequences, where the 3 sequence designs are shown at the top for reference. As expected, the relative efficiencies are all below 1 since the embedded staircase has fewer total measurements than its encompassing stepped wedge, and so we knew that it would be at least somewhat less precise. But in many cases, the staircase designs are not that much less precise than the stepped wedge. For example, for the 3 sequence designs with a small value of psi, the relative efficiencies are around 0.75 to 0.8, which is notable since the 3 sequence staircase has just half the total number of measurements as the stepped wedge. The relative efficiencies tend to decrease as the number of sequences increases. And we also see that the relative efficiencies drop down towards 0 as we approach SI approaches 1. So that's where the stepped wedge designs would be much more precise than the staircase designs. So then when we compare stepped wedge designs with extended basic staircase designs, where the designs being compared now have the same total number of measurements, we find that the majority of the relative efficiencies are above 1. So these results suggest that the extended staircase designs are typically more precise and would give greater statistical power than the corresponding stepped wedge designs for the same total number of measurements. However, for large values of psi, the relative efficiencies still drop down towards 0, and so in these settings, a stepped wedge design would still be more precise. And we do have some intuition for when the precision of the embedded basic staircase design will most closely rival stepped wedge, and it comes down to the forms of the treatment effect estimators for these designs. So it turns out that the treatment effect estimators for these designs and their precision are most similar when psi is small, and that's when we saw relative efficiencies that were closer to 1. And so for stepped wedge designs, Matthews and Forbes showed that the treatment effect estimator takes the form of a vertical estimator that predominantly relies on comparisons within columns or periods when psi is small and also when the number of sequences is small. And the stepped wedge estimator takes the form of a horizontal estimator that relies on comparisons within rows or within clusters when psi is large and when the number of sequences is large. But in our first staircase paper, we showed that the basic staircase design estimator always resembles the stepped wedge vertical estimator. So it relies on comparisons within periods. So the designs will have more similar precision when the stepped wedge estimator also primarily uses comparisons within periods, which occurs when psi is small. So in this final part of my talk, I'll show some results from 2 pieces of work that are aimed at developing a better understanding of which staircase design variants are a good choice for particular trial settings. As I mentioned earlier, many different staircase variants are possible, but there's currently no guidance on which ones are better than others. Among the possible types of variants, we could consider designs with an unequal allocation of clusters to sequences rather than an equal allocation. And moving beyond the basic staircase design, once we allow for more than 2 periods of measurement in each sequence, we could consider a balanced staircase design with equal numbers of control and intervention cells, or we could have an imbalanced set of control and intervention periods in each sequence. So first I'll cover our main findings from the unequal versus equal allocation of clusters work, and then I'll talk about when balanced or imbalanced staircase designs are best. To keep things simple, I'll focus on the 4-sequence basic staircase design depicted on the right. The default choice would just be to equally allocate a pool of n clusters to the design sequences, but here we wanted to determine what the optimal allocation would be if we could allocate clusters unequally to sequences. We made a simplifying assumption that the proportions would be symmetric, so that we'd be allocating the same number of clusters to the first and last sequences, and the same number to the second and second to last sequences. And then we had 2 constraints on our allocation proportions. The first constraint was that the proportions must sum to 1, and the second constraint that we imposed was that at least 1 cluster be allocated to each sequence. So we had a lower bound on each of these proportions. We wanted to preserve all the sequences of the design, but then we could allocate the remaining clusters however is best. And so then the goal was to find P1 and P2 that gave the most precise estimate of the treatment effect, which corresponded to maximizing the precision of the treatment effect estimator subject to our constraints. To do this for the 4-sequence design, I derived an expression for the precision of the treatment effect estimator, which looked a bit different from the variance expression I presented earlier, since now we're allowing unequal allocation of clusters to sequences. And then I used constrained optimization methods to derive expressions for the optimal proportions. And we got the results shown here for the optimal proportions plotted as a function of psi. And we see that these proportions really depend quite a lot on the value of psi. So for trial settings with a small value of psi, we get P2 being greater than P1, and so the optimal design would have more clusters allocated to the inner sequences. But then for larger values of psi, we have the opposite situation where P1 is greater than P2, and so we'd instead be allocating more clusters to the outer sequences of the design. And these results are fairly different from optimal allocation results for stepped wedge designs for a similar model, for which a design with more clusters allocated to the outer sequences is always optimal. And so what do these optimal allocation staircase designs actually look like? Say we had 20 clusters to allocate and we were in a trial setting with a small value of psi, which would arise when the cluster period size is small and the within period ICC is also small. Then the optimal design would look like the one on the right, with more clusters allocated to the inner sequences. But if we were instead in a trial setting where psi is large, which could arise with a large cluster period size, and when the cluster autocorrelation is also large, which means that there's not much correlation decay, then the optimal design would instead look like the one on the right, with more clusters allocated to the outer sequences of the design. So how much better are these optimal allocation designs than the equal allocation designs? To assess this, we calculated the relative efficiency, which we defined as the ratio of the precision of the treatment effect estimator under the optimal design to the precision for the equal allocation design. So then a relative efficiency greater than 1 indicates that the optimal allocation design is more precise than the equal allocation design. And for the 4-sequence basic staircase design, assuming categorical period effects, the relative efficiency is highly dependent on psi. For values of psi less than around 0.8, the relative efficiency is 1 or just above 1. And so the optimal allocation design is only slightly more precise than the equal allocation design. But for values of psi between 0.8 and 1, the optimal allocation design is much more precise, up to 60% more precise than the equal allocation design. And so it's in trial settings with a large value of psi where the optimal design would be most beneficial. So again, when would we find ourselves in that setting? Returning to the contour plots from earlier, we see that large values of psi between 0.8 and 1 tend to occur in this highlighted region shown here, where we have a large cluster period size, large cluster autocorrelation, and moderate value for the within period ICC. So the within period ICC is less influential for larger cluster period sizes, but as long as that within period ICC is not very small, we would end up with a large value of psi. And so it's in these settings where the optimal design would be most useful And the optimal design for large values of psi has more clusters allocated to the outer sequences. And then looking at the optimal proportions for 6-sequence basic staircase designs, we see a similar pattern as for the 4-sequence design. So with more sequences, we have more proportions. And so the main difference is that only the proportion to the outermost sequences starts small and gets larger as psi increases, whereas the proportions to the inner sequences start out larger and then get smaller as psi increases. We still get, where these proportions cross over at some point along there. And so finally, we'll look at when balanced or imbalanced staircase designs would be preferred on grounds of efficiency. And we'll see that these results also depend a lot on that psi parameter. So here we have a 3-sequence staircase design with 4 measurement periods in each sequence. And this is a balanced design with equal numbers of control and intervention cells in each sequence. But we could potentially have an imbalanced design with either 1 control cell followed by 3 intervention cells, or 3 controls followed by 1 intervention. And so then the question here is, which of these designs is most precise? Well, it turns out that these 2 imbalanced designs are actually equally precise. And we're able to explain why by referring to certain properties of the matrices and the precision expression, but I won't get into the details in this talk. Generally, though, if we swap the zeros and ones and reverse time, then the resulting design will have the same precision as the original design for the model that we consider. So how does either of these imbalanced designs compare to the balanced design in terms of precision? We'll look at the relative efficiency, which we now define as a ratio of the precision of the treatment effect estimator for the imbalanced design to the precision for the balanced design. And so a relative efficiency greater than 1 indicates that the imbalanced design is more precise than the balanced design. Looking at a plot of the relative efficiency as a function of psi, we can see that the relative efficiency increases as psi increases. So for small values of psi, the relative efficiency is less than 1, meaning that the balanced design is more precise. And then for larger values of psi, the relative efficiency is above 1, indicating that the imbalanced design is more precise. In particular, the imbalanced design will be more precise than the balanced design when, in this case, psi is greater than 0.282. So this is the psi threshold corresponding to designs with 3 sequences and 4 measurement periods in each sequence. But for designs with more than 3 sequences, we get slightly different results. So here are the relative efficiencies for designs with 4, 5, and 6 sequences as well. For each of these designs, we still see the relative efficiency increasing as psi increases, but as the number of sequences increases, that psi threshold also increases. And so there are progressively fewer trial settings where an imbalanced design would be more precise, and we get that a balanced design would be more precise in more of the trial settings. And so it's useful to see how the relative efficiency depends on psi, since psi encodes information on the cluster period size and the underlying individual level correlation parameters. But we can also see how the relative efficiency depends on these underlying parameters as well. So here are the same results for the 3-sequence design with different cluster period sizes in the top and bottom panels for a range of realistic correlation values with the within period ICC along the x-axis, and then different cluster autocorrelation values in the lines of this plot. So we can see that the relative efficiency increases as each of these 3 parameters increases. So when we go from a smaller to a larger cluster period size, as the within period ICC increases, and also as we increase the cluster autocorrelation, so we go from lighter to darker blue lines. And here are a few more configurations for designs with 6 and 12 sequences as well. So the preferred design really depends on the trial setting and of sequences. We can see for 12 sequence designs with a small cluster period size, for the designs with 4 measurement periods in each sequence, a balanced design is always preferred here, but for the 3 sequence designs, an imbalanced design would typically be more precise than a balanced design. In summary, staircase designs are pragmatic and less burdensome alternatives to stepped wedge designs. We've developed underpinning statistical theory for these designs to support accurate sample size and power calculations. And some existing software that can be used for stepped wedge designs can also be used for staircase designs. But the main requirement is that it would need to allow for specification of incomplete designs, which not all software does allow. From all of our design efficiency work so far, we've found that there really is no definitive best staircase design, since the efficiency depends so heavily on the trial setting. For example, there were certain trial settings for which a basic staircase design was more efficient than a stepped wedge. That typically required allocating more clusters to the sequences. Staircase designs with optimal unequal allocation of clusters were much more efficient than the equal allocation designs in some settings, but in other settings they weren't very different in terms of their precision. And we also saw that balanced designs were more efficient in some settings, while imbalanced designs were more efficient in others. But rather than simply concluding it depends, we can do a little bit better than that. So here I've attempted to summarize the design efficiency results by breaking the trial settings into those with a small value of psi and those with a large value of psi. So for trial settings with a small value of psi, where we tend to have smaller cluster period sizes, less similarity between participant outcomes, and more waning of similarity or more decay over time, then we tend to see these types of designs being more efficient. So in the comparisons between staircase and stepped wedge designs, we saw the stepped wedge was still more efficient than an embedded basic staircase, but we already knew it would be. But in some settings, for small values of psi, the relative efficiency wasn't actually that far from 1. So an embedded basic staircase wasn't that much less precise than a stepped wedge design. When we compared extended basic staircase designs to stepped wedge designs, we saw that the extended basic staircase designs were much more precise for small values of psi than the stepped wedge. We also saw that staircase designs with an unequal allocation of clusters to sequences, with more clusters allocated to the inner sequences, was slightly more precise than the equal allocation design, but not that much more precise. And we saw that for small values of psi, the balanced staircase design tended to be more precise than the imbalanced design. And then in situations with a larger value of psi, which would typically arise with larger cluster period sizes, with greater similarity between participants' outcomes in a cluster, and less waning of similarity over time, this is where we saw the stepped wedge was still much more precise than the embedded basic staircase design and the extended basic staircase design. We also saw that for basic staircase designs with an unequal allocation of clusters to sequences and more clusters allocated to the outer sequences, those designs are much more precise than the equal allocation designs. And we also saw that imbalanced staircase designs tended to be more precise than the balanced designs. So this helps to summarize those situations where we'd have definitely a smaller value of psi or a large value of psi, although for moderate values of psi in between, we'd still at this stage have to say it depends, because we saw that those designs really, those comparisons were not definitively pointing to one design over another. And so the work that I've presented forms a strong foundation of knowledge about staircase designs. But there's much more work to be done to understand them to the same extent that we now understand stepped wedge designs. My team and I have recently looked at the cost efficiency of incomplete stepped wedge designs. And in this work, we've seen that staircase designs do emerge as particularly cost-efficient variants. And we're also aiming to develop a better understanding of the vulnerabilities of staircase designs by looking at how trial conclusions would be impacted when things don't go according to plan, such as when we misspecify the form for the similarity within a cluster, if clusters were to drop out during the study, and if we have limited trial data, which could arise from having a small number of clusters. And I also plan to extend the theory from batched stepped wedge designs to batched staircase designs, which would allow for clusters to be recruited in batches rather than needing all clusters to be ready to go at the start of the trial. So finally, I'd like to thank my collaborators on this work, and happy to take any questions next or also by email. Thank you very much.
Thank you very much, Dr. Grantham. Very interesting presentation. We've got a number of questions coming in from our viewers, and so let's just get started with them. There's considerable interest in this parameter psi, um, which represents the correlation between cluster period means. How can we plan a trial if we don't know the appropriate value for psi? How can we get an estimate for an appropriate value of psi? Any thoughts on that? It seems to play such an important role in this staircase design.
Yes, it does. That's it's a really important question. So yeah, psi depends on cluster period size and on the underlying correlation parameters. And it's really, I mean, cluster period size, we would know, that's just the number we could feasibly measure in these cluster periods. But it's really the correlation parameters that are harder to get good assumptions for. So there are some tools now that compile some of the estimates from other studies that you can sort of refer to see if there's a similar study that you could get a good estimate for your correlation parameters from. So for example, there's the CloudBank repository that now has sets of correlation parameter estimates from different studies. So that would be probably the first place that I would go to see what types of correlation parameters we'd be likely to encounter. And then in terms of translating that to psi, then I guess you'd need to sort of take your cluster period size and your plausible values for the correlation parameter values, and then actually see what values of psi you would be getting from that. And then try to kind of go from there to see if that points towards certain designs. For any particular trial setting, I mean, you can still explore all of these different variants yourself. But really what we're trying to do is just provide broader rules of thumb about which types of designs are best in certain settings.
Thank you. That's helpful. We have someone asking, when might one want to use a design with more controls than intervention participants? Now, I'm not sure I understand the question, because in this design, everybody's going to be in both control and intervention, but perhaps the question will make sense to you, or the questioner will put something else in the chat.
Yes, I interpreted that to mean, when might we prefer, say, this particular imbalance design over this one, so that we'd be measuring participants under the control condition for more periods than under the intervention.
That seems like a perfectly fair interpretation.
So,
please.
Yeah, so we may, I mean, in some settings, we'd be interested in getting a good sense of kind of what the baseline measurements are like. There's also, studies that are interested in pre-implementation versus post-implementation results. So I think it's probably more likely that you'd be interested in following the cluster under intervention for more periods if you were considering an imbalanced design. And I suppose when in the trials that have already gone ahead that have used a staircase-like design, they do tend to include more intervention cells than control cells. So yeah, I imagine there are situations where you'd want more control cells, maybe, but probably you tend to want more intervention cells in your design.
Thank you. Having more intervention cells, more observations under intervention for more periods, raises the specter of time-varying intervention effects. And we have someone in the audience who asked, can you speak to how different designs compare in their ability to adjust for time-varying intervention effects? We've seen that can be a real problem with standard analytic methods applied to step wedge trials.
Yes, that's a great question. So the model that I presented assumes an immediate treatment effect. So it assumes that we are under the control, and then as soon as we switch to the intervention, that intervention effect sort of switches on and remains constant over the remainder of the trial. And so there is a body of work in the past few years that's showing that if if instead it was more plausible that the intervention effect might vary over the exposure period, so over those periods under the intervention, then we would need to account for a more complex interventions or trajectory in order to get the effect that we're interested in. That raises the question of which estimand are we interested in? Are we interested in the sort of time average treatment effect, or maybe if we think it will sort of the effect would ramp up and then stay constant, then maybe we're interested in the long-term effect. And so this actually raises some really interesting questions in terms of which staircase designs would be best for being able to estimate those kinds of effects. So obviously, if you think that your intervention effect is going to be changing over time, then a basic staircase design with just the one control and one intervention cell probably won't suffice, because you're only then gathering information from the clusters under one intervention period. So you would definitely need to follow those clusters over more intervention cells. So then thinking of maybe a design like this, where we have more follow-up under the intervention. Then there's another sort of complication here, which is that I mentioned basic staircase designs rely on just comparisons within periods, so within columns. And we have seen also that designs with more than two measurement periods in each sequence still rely more on the comparisons within periods than within clusters. And so then we need to think about which designs would actually give us enough comparisons within periods to be able to estimate a longer term effect. So if we were interested in the effect, say, after these 3 exposure periods, we actually don't have any, in this design for 3 sequences, we don't have any control cells to compare those intervention cells with in this period. So even though we're following all the clusters up over those 3 periods, we actually don't have much to use to estimate the effect at this point. So we would at least need to include more sequences so that we'd start to get some control cells in these periods to be able to compare it with. The question is, how many sequences do we need? We'd still need to explore that. And then the other question is, would a balanced staircase design actually be better than an imbalanced design, because it's providing more control cells to compare within periods to the intervention cells? So we don't have any definitive answers on this yet, but it's actually, there's a lot more to consider, because there's this kind of degree of freedom with which staircase design do we use. Whereas with the stepped wedge, it's more of a fixed schematic, although we may still want to extend the number of periods to make sure that we've followed up enough clusters to get those long-term effects. There's really a lot to consider here, and we definitely need to look at this more.
Another thing to consider is the timing of the measurements. If the measurements are every few months or every 6 months or something like that, and you have a lot of them, then certainly you could observe a time-varying intervention effect. If you think the intervention effect is going to peak at a year, you could just schedule your measurement at a year and not have the other measurements and not worry about a time-varying intervention effect. Just try to get it when it's optimal. But that requires knowledge of the pattern, and often we don't have that. So it's there. Yeah, there's a lot to consider, and it can be complicated.
Yes.
Yeah, you have. I don't think you spoke to the question of do things change if you have a basic cohort design versus a cross-sectional design. So if you're measuring the same participants over time versus measuring different participants at each period.
Yes. So you're right. I didn't address that. I looked at just like the cross-sectional measurement scheme only. But we have looked into this enough to know that if we had a cohort design, then we'd have that would give us another correlation parameter, because that would be the correlation between the repeated measurements on the participants. And so from the perspective of this psi parameter, that actually just becomes another term within this psi parameter. So we can still sort of define a new version of psi that rolls that term in with these other correlation parameters and our cluster period size. And so actually the relationships as a function of psi that we've seen still hold, but under cohort designs, because we then have an additional parameter in the psi function that would tend to increase the values of psi that we would be seeing. So the value of psi under a cohort design would tend to be larger than the value of psi under a cross-sectional scheme. And so that kind of pushes things towards larger values of psi. We need to do some more work to see kind of how much that pushes things for sort of common situations with cohort designs and common correlation parameters. But fortunately, the results as a function of psi still hold in that situation.
Thank you. Have you looked at implications for having a binary outcome or compared to a continuous outcome? I suspect that the basic work has been done with continuous outcomes.
That's right. Everything so far has focused on continuous outcomes, but that is definitely on the agenda to look at and try to see how some of these results change for binary outcomes. We wouldn't expect some of these kind of comparison type results to change too much for binary outcomes, but we do need to assess that further to make sure these same kind of relationships hold.
There's a design that I've used in the past and suggested to others to use occasionally that has some similarities to this staircase idea, but I haven't ever thought of it as a variation on a step wedge design. Let's say you've got it's a form of a parallel group or cluster randomized trial. I sometimes refer to it as a staggered start parallel trial, where you've got the most recent example that I worked with, for example, the team had 42 churches and they were going to randomize half to intervention and half to control, but they were scared to death of trying to launch all of them at the same time. And so they divided the 42 into 7 sets of 6 and started with the first set of 6, half intervention, half control. And once they were launched and the intervention was underway, then they launched the next set of 6 and so forth. So over a period of time, all of the sets of 6 got launched. They ended up with data from 42 clusters, 42 churches, and they always maintained the control clusters in the control condition, the intervention clusters in the intervention condition. They just avoided the burden of trying to launch all of the clusters at the same time. Have you compared the staircase design to this parallel staggered start design?
I haven't yet, but I certainly will. That seems like it'd be worth seeing how different they are, especially in terms of efficiency from the efficiency perspective. Yeah, so that is an interesting type of design, and yeah, I don't think it would fall under the staircase design classification, but it is similar in many ways with the sort of staggering over time, and still sort of having some control and some intervention measurements. So I will certainly have to look into that.
All right. Another question, in the setup of the data that you were talking about and the models that you were using, you allowed 2 different levels of cluster or of ICC, I think. There's one level within for participants measured in the same period, and a different level for participants measured in different periods. Yeah, there it is. Yeah. The value of R there is presumed to be the same for any participants measured in 2 different periods, no matter how far apart the periods are. And we know that in some situations, the value declines as periods get further apart. Is that something that needs to be considered in these staircase designs, or do you avoid having to deal with it because the staircase doesn't have so many periods that are very far apart?
Yeah, that's a great question. So if we're just thinking about a basic staircase design, then we really just have those 2 periods of measurement in each sequence. So there's really not much opportunity for correlation to decay over time. So in those settings, this type of structure would, still account for decay from the one period to the next, but that's really as finely grained as you need to get when there's just the 2 periods. But it is a valid consideration when you're thinking of designs with more than 2 periods of measurement in each sequence, so that it does allow the potential for the correlation to decay over time. And so in those settings, we might consider a discrete time decay correlation model. And we have considered that in work that's involved more than the 2 periods of measurement in each sequence. Typically, the results don't seem to be too different from this sort of simpler model with just the 2 levels. But I think if you were planning a study, you would want to definitely, make sure your trial was adequately powered in case the decay did continue to have an effect over several trial periods. So it is still something to consider. But yeah, due to the limited number of measurement periods in each sequence, there's also a little bit less opportunity for that decay to take place.
We have a few questions related to power sample size calculations. One, would the sample size calculation and power be the same formula for the balanced design and the unbalanced design?
Same formula. Yeah, so the variance of the treatment effect estimator factors into a power or sample size calculation. And so it's in here that you have these sort of X vectors that have the composition of your treatment sequences. So an imbalanced design, may have the X vector has a 0 and then 3 1s versus a balanced design would have 2 zeros and 2 1s. So that can, each of those designs can feed into this same expression that can then calculate your power. So it turns out that I mentioned that certain imbalanced designs were equally precise. So it's actually this kind of matrix formed by all of these other terms that has some special kind of symmetry properties. That means that if we summed all the elements in one submatrix, that's actually the same as if we summed the opposite side of the matrix. So yeah, I would think you can use the same expressions and the same calculations for those different designs.
Another question related to sample size and power has to do with resources, whether web-based or otherwise, for sample size calculations for staircase designs. Are there sites that people can go to that would allow them to use a web-based calculator to look at different variations and compare sample size requirements or power availability?
Yes, and so I mentioned there are some that currently allow for specifying an incomplete stepped wedge design. My sort of go-to tool at the moment is the Shiny CRT calculator, which is just an online tool. And in that tool, you can upload your own design matrix. So you basically just create the design matrix in an Excel spreadsheet, and you can upload that with your sort of zeros and ones and any gaps in the design, and then it will calculate your power from there. So you can certainly input any kind of staircase design with that tool. And there are a few other tools built in, or packages for R and tools in SAS that do also allow for an incomplete stepped wedge to be specified, but the syntax is different for each one. So in some cases, you have to sort of specify the cells to exclude from the stepped wedge, and so you just have to be very careful to make sure you're getting the design that you think you're getting, to make sure that the power works out. Otherwise, there is, I provide code with my papers that you could also use to calculate your power or sample size requirements.
And is the Shiny app that you're referring to the one that I associate with Carla Hemming?
That's right, yes.
Yeah, all right. I'm going to put the link to that in the chat box so that people can get to it if they're interested.
Yes.
Yeah, there it is. Okay. So that's we have spoken about that website previously as a good place to go to do sample size calculations for different kinds of clustered designs. And it sounds like Staircase fits that, perhaps not quite as menu driven. You have to put in your own design matrix, but with that, you can do it. I want to thank you very much for your presentation today and this interesting discussion that we've been able to have. We've reached the top of the hour, so I'm going to turn things back over to Dr. Moyer.
Thank you, Dr. Murray, and thank you to everyone who participated in today's webinar. On the Mind the Gap website, prevention.nih.gov/mindthegap, you will find several resources for this talk, including the slides and a list of references. We will also be posting a recording of today's webinar on our website in a few weeks. Thank you and have a great rest of your day.